Welcome. Today's episode of Eating Cereal features a lesson on gravitational spaghettification and what food goes better with gravitational spaghettification than a big bowl of spaghetti. This includes noodles, sauce, onions, jalapenos, and of course cheese. And I weighed this out on the human size scale before I got started here, and according to that it weighs 11 pounds. I don't know how accurate it is, but this is going to be a lot. I haven't done a food challenge in about 2 months, or any kind of big time eating in that amount of time. So this will be tough, but I'm gonna give it everything I've got, and it'll be fun. Alright, let's get started. The starting time is 4:51. Let's do it. Since I'm eating all this spaghetti today, I'm going to make today's lesson about gravitational spaghettification. So I'm a huge fan of Dr. Neil DeGrasse Tyson, the astrophysicist. I've read nearly all of his books, and I could just listen to him lecture all day on astrophysics. I think he's great. And one topic he talks about quite a bit is black holes and what would happen if a human were all of a sudden put into a black hole. And he gives a really good lecture about that, and the answer is spaghettification. Human spaghettification is what would happen. So first I want to talk a little bit about the anatomy of a black hole and what a black hole is. A black hole is the remnant of a large star that has exploded, and it is a very dense collection of mass, far denser than anything that we've ever encountered. And what we have is a density distribution throughout the black hole, and the density approaches infinity as you get towards the center, and this is called a gravitational singularity, and it is a point at which the known laws of physics just don't apply anymore. So we don't really know what happens at the gravitational singularity of a black hole, and if you haven't seen the movie Interstellar, plug your ears for about 10 seconds. But in that movie, they predict that what happens is you go into a space where you have control over time dimensions and can influence things that happened in the past, which is, I thought it was a great movie. So it may or may not be true, but it was a great movie. So the escape velocity of a black hole is greater than the speed of light, which is why not even light can escape a black hole. The edge of the black hole is called the event horizon. And I think the reason that it's called that is because any event that occurs within the edge of this black hole will never be known to anybody outside of the black hole. So the light that would come off of the objects in this event will never actually make it outside of this black hole. The photons cannot travel fast enough to escape. And the distance between the center of the black hole and the edge of the black hole is called the Schwarzschild radius. So here's what would happen if a human all of a sudden found themselves in the center of a black hole, or not even in the center, but on the edge, near the event horizon. And it's worth noting that this has never happened to a human. Hopefully it won't happen anytime soon. The furthest any human has traveled from the Earth were the Apollo missions, Apollo 11 through 17, where we went to the moon roughly 250,000 miles from the Earth. And the nearest black holes that we know of are a couple thousand light years. We're talking on the order of 12 to 18 quadrillion miles. So we have not traveled nearly far enough from our Earth to get into the event horizon of a black hole where this would happen. But here's what would happen if a human all of a sudden found themselves near the event horizon of a black hole. First of all, you have the gravity equation right here, and gravity is the force that attracts two massive objects. You've got a person here, and you've got the black hole. The center of the black hole is where the gravity and the density of the black hole approaches its singularity, it approaches infinity. So we've got a human here. We're going to say this human is 2 meters tall and 100 kilograms in mass. So and we're also going to assume this black hole has a radius of 100 meters. And what I'm going to show here is that the gravity pulling on this person's toes is massively greater than the gravity pulling on this person's head. And if you can see the numbers getting worked out here right now, if you're in this black hole, the mass equivalent is the equivalent of 50 Empire State Buildings. That's the difference in force between G1 at your head and G2 at your toes. So it's like being suspended on a pull-up bar as 50 Empire State Buildings are hung from your toes. So it's obviously more force than the human body can handle. It's a more force than the molecular forces that hold together the cells in our bodies. So your body gets ripped in half. Move forward a few more, let's say microseconds, maybe even nanoseconds. This happens very quickly. And this happens again to these halves. So all of a sudden your halves are split into quarters. And then this keeps happening and you're getting even closer, and the gravitational offset becomes even more significant as this radius value gets smaller and smaller. The gravity becomes insanely intense. And by this point you're already dead, but what's happening to your body now is it's becoming these long molecular or just atomic width strands of spaghetti. Not actual pasta spaghetti, but they're like spaghetti in that they're just become these long strands, and you got billions and billions of them. What your body once was has now just become these long strands of atoms, and therefore you have spaghettification. So I recommend listening to any lecture, well, really any lectures that Dr. Tyson gives, and this is a particularly interesting one. And he also has a book where he discusses all the mathematics behind it. The book is called Death by Black Holes. So it is a very interesting book, interesting topic as well. All right. That's it for the spaghetti. 29 minutes maybe. Not too bad. I don't think it actually weighed 11.2 pounds. What I think happened is, to even get it to register on the scale, I had to drop it onto the scale, and that initial shock threw off the numbers. I think it was more like 6.5 or 7 pounds. But yeah, it was good spaghetti, and I'm still a little hungry. I think I'm gonna have some ice cream, but I'm gonna eat it slow though, so I'm gonna put it on a time lapse. So one more thing I want to cover is we live on planet Earth, and I just want to go over why does spaghettification not happen to us on Earth. And the answer, there's a couple of answers. First of all, the radius we are from the center of the Earth is roughly 4,000 miles. As we're standing here on the surface, we're about 4,000 miles from the center. Unlike this black hole where you can get within the Schwarzschild radius and you are all of a sudden, and this is a smaller black hole, but in this one we were only 100 meters from the center, so the gravitational difference was insane. Here, so let's say your toes would be 4,000 miles away from the center of the Earth, whereas your head would be 4,000 miles plus 2 meters from the center of the Earth. So the difference there, for one thing, is not very significant. Also, the mass of the Earth is basically nothing compared to that of a black hole. So even a black hole as small as this is way more massive than the Earth. We're talking about a couple thousand times the mass. Even a black hole with a radius of 100 meters is several thousand times the size of the Earth. Not the size of the Earth, but the mass of the Earth. So you may be asking, well, let's say we got closer to the center of the Earth. So let's say we drilled a hole through the center of the Earth, which is already pretty dangerous. So you're going to die from other reasons if that happens. But if you do that, you could potentially get to the center of the Earth, make this radius value small, so that these gravitational differences once again become very significant, because the gravity acts pretty much from the center of mass of the object. And the reason why this is not going to work is because the density distribution of the Earth is fairly uniform. So once you get to the center of the Earth, you've got just as much force from gravity pulling you from, let's say, the north side of the Earth as you do from the south side. So you're not going to get spaghettified. You will get burned up by all of the magma and iron. So that will do it for this lesson on spaghettification, and let's see if I can finish the rest of the spaghetti.
All right, all done. See you next time.